So today we are going to read Chemical Reactions by Jenna Winterberg. Everyday chemistry. When we think of chemistry, it's hard not to picture a lab with students wearing coats and goggles and using flasks and burners. But chemistry doesn't just happen in school. It regularly occurs all around us. Take breakfast, for example. Maybe you ate an egg or a piece of bread. Those foods are created through chemistry. And the way your body takes those foods and turns them into energy is another example of chemistry at work. In these cases, it's a chemical reaction. In other words, a change takes place that alters the material's makeup. The raw egg changes when it's scrambled or boiled. The food changes when your body digests it. Chemical reactions are such a normal part of our lives that we hardly note when they take place. We take for granted that when we put gas in our cars, it will fuel them. We don't think about science when we bake cookies or cakes. And chemistry is the last thing on our minds when we're warming ourselves by a wood-burning fire, watching fireworks up in the sky, or admiring the changing colors of autumn leaves. But without chemical reactions, none of these things would happen. Combining substances. Fresh cookies don't just appear out of thin air, don't we wish? You have to combine ingredients first before you bake them. For any chemical reaction, you need ingredients. In this case, we call them reactants, because they are going to react to a chemical change. In baking, reactants are things such as sugar, eggs, and flour, but they could be just about anything, from oxygen or water to copper or salt. Atomic number, element name, oxygen, chemical symbol, O, atomic mass. Atoms are rarely single. Atoms, the smallest bits of matter, make up everything around us. They bond with other atoms to create molecules. Atoms are attracted to other atoms based on the number of electrons they have. There's a water molecule. The simplest form of reactant is an element. An element is a substance that contains only one kind of atom. For example, oxygen is an element. Water is made up of two kinds of elements, oxygen and hydrogen. When two or more elements bind together like this, the result is a compound. Compounds can be reactants too. There are far too many compounds to list them all, but the number of elements is limited. We make sense of them by way of a chart called the periodic table. The chart organizes the elements by atomic number. That's the number of protons in each atom. It also contains the atomic mass, the number of protons plus the number of neutrons. Chemical reactions don't happen every time two substances combine. Sometimes the combinations simply form mixtures. In these cases, a physical change occurs, not chemical. A physical change can affect the way a substance looks, such as its size, shape, or color. Sugar will dissolve in water. When combined, they form a type of mixture called a solution. But the sugar and water have not changed chemically. In fact, they can still be separated. Plain cookie dough is another solution. You've mixed flour, sugar, butter, eggs, and other things to make the dough. This mixture would be difficult but not impossible to separate. Still, no chemical change has taken place. All gas mixes are solutions. Take the air we breathe. It contains oxygen, sure, but it also has other elements such as nitrogen and compounds such as carbon dioxide. There are a total of 15 gases in our air. Solutions are just one kind of mixture. They're homogeneous. In other words, all of the parts are evenly mixed and completely spread out. You can't see or tell one part from another. Your plain cookie dough is a homogeneous mixture. Other mixtures are heterogeneous. They contain a little more of one part than another. You can easily see the different parts of the mixture. If your cookie dough had pieces of chocolate that you could see or even pick out, it would be heterogeneous. sweet alternative. A colloid is a special type of homogeneous mixture. It has larger particles than a solution, but they are still evenly spread out. Tricky mixing. A mixture can always be separated. If it can't, then a chemical reaction has taken place. Even solutions such as sugar dissolved in water can be separated. Simply boil the water until you are left with just the sugar. Sometimes it just takes a special tool. So think hard before you say that your mixture can't be reversed. Homogeneous, heterogeneous. Examining properties. When we combine substances, we want to know what changes. We get this data by observing and measuring. You might note that a mixture is pink in color. That's a good observation. But would it mean more if you knew the colors of the original substances? If they were white and red, pink is no surprise. But if they were white and blue, it's an exciting result. To make sense of mixtures, we need to understand individual parts first. That's why we measure and observe before and after. We look for a number of things when observing, but we always start with physical properties. These are things we can assess without altering the substance. Weight, volume, length, color, hardness, and smell are all physical properties. Magnetism is another example. So is the density of an object or how compact it is. We might even consider whether an object can conduct heat or electricity. The temperature at which a solid becomes liquid, its melting point, is another physical property. So is boiling point. When liquid becomes gas. When water turns to ice, the phase change doesn't alter its chemistry. It's still hydrogen and oxygen, just colder and solid. It's a phase. Chemistry has its own term for each type of phase change. A solid to a liquid is called melting. An example is ice to water. A liquid to gas is called evaporation or vaporization. Water to steam. Solid to gas, sublimation. An example is dry ice to gas. A gas to a solid, deposition. Water vapor to ice. Gas to liquid, condensation. Moist air to dew drops. Liquid to solid, freezing. Water to ice. Substances can also have chemical properties. These properties describe the substance's potential to react with something else. In other words, chemical properties tell us if a substance could be a reactant. The chemical properties we might measure aren't standard. There isn't a set list that we check off. Rather, what we measure depends on what we want to study. Often, our focus is on whether a material will react in response to acid, water, or air. Maybe we want to know if something is flammable. Will it burn when oxygen is present? Maybe we want to know just how flammable it is. How long will it burn? Perhaps we want to test if it will explode when ignited. We might like to see if an object will rust. Other times, the question might be if it will turn into another substance. When observing physical properties, no changes are made to the substance, but in these examples, there is a risk of altering the original substance. It is the only way to test a substance's chemical properties. In all these cases, we are actually looking to see whether a chemical reaction will occur. Chemical evidence. Scientists examine chemical properties of evidence to solve crimes. They can use chemical properties to identify chemicals, poisons, or small bits of evidence left on the scene. Creating a product. Every chemical reaction will produce at least one new compound. This new substance is called the product. The product may be physically different from the original substance, and it is always, in some way, chemically changed. When two or more elements combine to form a compound, a chemical reaction takes place. For example, hydrogen and oxygen are two reactants that combine to form water. The compound is the product, which in this case would be water. It's quite different from the two gases that combine to form it. Compounds can also react to form a product. Take potassium iodide and lead nitrate. Both are compounds. Both are colorless liquids. Combined, they form a solid yellow substance called lead iodide. This new compound is the product of a chemical reaction. Chemical reactions aren't limited to the lab. When we boil a raw egg, it transforms. The egg is chemically changed. The boiled egg is a product and will never return to its previous composition. Likewise, when we place cookie dough in the oven, its chemical composition changes. The baked cookies taste and smell different from the dough. These are clues that a chemical change has taken place. Our product is freshly baked cookies. We use chemical reactions to make cars and rockets go. Rockets get their power from a chemical reaction that occurs when liquid hydrogen and liquid oxygen are combined. Chemical shorthand. Scientists write out reactions in symbols. They're a little like math equations, but here the numbers become elements and compounds. First, reactants add together. Then, an arrow leads to the result. For example, hydrogen plus oxygen equals water. Using chemical symbols, that equation looks like this. H2 plus O is H2O.